Section 6.3 is about arc length. So now consider an arbitrary curve, y is equal to f of x, and we are interested in finding the length of this curve. But how would you do that? You would just divide this arc into pieces. So we are going to have this P0, P1, P2, P3, P4, blah blah, Pn pieces. And for each dot, these are dots on the curve, okay? We know the coordinates of each curve here, of each point here. And then what you do is you just find the length of the line segments between these points and then approximate them. Okay, you get an approximated value for the length of the curve. Okay, so let's say just pick 2 points on there, which is xk, pk minus 1 is the point, and xk minus 1 is the x coordinate of that, and pk is another point, and xk is the x coordinate of that point, and lk is the length in between. Okay, so this is going to be delta xk, this is going to be delta yk, right? And if you square this with this, because you have a right triangle, if you square them, take the square root of the sum, you get lk, right? Lk is equal to square root of delta xk squared plus delta yk squared, right? It is the distance between pk and pk minus 1. Okay? We are talking about this arc, and this lk is the approximated value of that arc. It's not the exact value, but it's approximated value. So we are going to consider all of such, and then we are going to get the formula. The formula actually, it doesn't look very much like the other one. Okay, so we have that. But what you do is you divide both sides with delta xk, and we have delta yk over delta xk squared, which is similar to the f prime, the derivative of f at x, and we are going to have 1 here, and this is going to be lk over, okay, delta x, right? So okay, and then if you multiply that, okay, this is that part times dx, you're going to get the actual length of the curve between the points A and B, right? Capital A and capital B. So we have this f prime, you can consider it dy dx, you take the derivative of that. Okay, so A to B, square root 1 plus the derivative of y with respect to x, take the square, dx is going to give you that. For example, we are interested in the length of the curve, okay, joining A and B. So how would you do? We have a formula, we have a function here, y is equal to 4 over square root of 2 over 3, x to 3 over 2 minus 1. And then we use our formula, and x is changing from 0 to 1, and square root 1 plus, take the derivative of this with respect to x, and then square that, and times dx, integrated, and you get the exact length from A to B, alright? And so we are interested in length of the curve between A and B. Okay, how would you do? X is going to go from 1 to 4, so we are going to say integral from 1 to 4, square root 1 plus the derivative of this, take the derivative, and then square that, and times that dx, and you just integrate that. Okay, if you have the graph of the curve is given in terms of x is equal to g of y, nothing is actually changing, and y is between c to d. The length of the curve between the points capital A and capital B is going to be square root 1 plus, instead of dy dx we have dx dy squared, and then we integrate over dy. So it's the same, c to d squared of 1 plus g prime y squared dy. So nothing is really changing very much, but I mean it's easy to understand if we have the situation like that. This is an example to that fact. The graph of this is given as y is equal to x over 2 to 2 over 3. and we want to find the length by using by integrating over y. So we can integrate either we can use g of y as this 2 times y to the 3 over 2 and integrate from 0 to 1 over y, or you can use x values and then you integrate over 0 to 2 square root of 1 plus y prime dx, right? You can use either way. Okay, I think that's good enough.